Welcome back to biodegradable materials, or biotechnology and biodegradable materials. Today we're going to consider oxo-degradation. So oxo-degradation is a case when oxygen degrades our polymer, and we can do it deliberately, but it also happens accidentally. It's one of the main problems with recycling plastic bottles. So if we look at this particular reaction, we have oxygen interacting with a carbon-hydrogen bond, doing a Diels-Alder cycloaddition, which you might know, where there is a ring of electrons. So there's a ring of bonds, in this case a square, forming and breaking. So this bond moves to here, this double bond moves to here. This is not the actual mechanism. The mechanism is quite complicated and it's unclear. But the actual result is the same, is correct. That's a hydrogen over there. Let me move my camera slightly. That's a hydrogen on the end. So we formed an internal peroxide of our molecule. So it either goes by this mechanism, it goes by a different mechanism where the end of the oxygen comes up, or it goes via a radical, via the hydroxy radical here with a hydrogen on here. So the hydrogen is first abstracted and then this group attacks. But our resulting polymer has now a peroxy side chain. When does this happen? In normal cases, it happens when you heat up the polymer in the presence of oxygen. Why is that? Well, this cannot attack, normal oxygen cannot attack, as we know. Only singlet oxygen can attack, because the place where this electron is going to go in is already filled with a single electron. In a normal oxygen, the singlet oxygen has one electron in this antibonding orbital and one electron in the other antibonding orbital, so we cannot give two electrons to it. That makes it a lot more difficult and a lot less reactive. So oxygen usually only reacts when it's been excited with light or when it's hot, so that these other energy states with a empty orbital in the antibonding orbital here are in fact active. The singlet oxygen is way more reactive than the triplet oxygen. Which the triplet oxygen is the normal state with two single electrons in the antibonding orbitals. So typically we'll have formed this peroxide during production of our polymer, and it will be present, or it will happen in the presence of ultraviolet light and oxygen, because that is when we get singlet oxygen, as you will recall from physical chemistry. Other people can have a look at our course on physical chemistry to see that singlet oxygen is a compound, is a product of ultraviolet light, some chemicals and oxygen. That causes it to be more reactive and interact with bonds much stronger in a variety of ways. This is not, again, not the actual mechanism. There are several proposed mechanisms, but because it's complicated, we will start from here, because the more important thing to us is the rate determining step, which is weirdly not this one. So if we take a normal polymer that has been recycled a few times, or it's been overheated, whatever has happened, or it's stood in the sun for a while, we would expect it to have a small amount of this peroxide present by whatever mechanism it's formed. And this peroxide can break down to form two radicals. This bond can break to form two radical species, the radical oxide here of the polymer and an OH radical. This is the slowest possible step in our reaction, because we're making two radicals out of a unstable but a chemical species that is at least reasonably stable. So if we consider the reaction of breaking down normal polymers, any normal polymer including polyethylene, this is a critical step in there, and this is the slowest step, although the peroxide will usually have been formed during molding. So oxo degradation is a common theme also in normal polymers. So we take, for example, polyethylene and we leave it in the sun in the presence of oxygen. It will do this. We can make this reaction faster by increasing the concentration of this component, which will make this step faster because there's just more of it, or we can catalyze this part. Obviously, the formation of two radicals is very energetically intensive, and the radicals aren't very stabilized inside a polymer because there's nothing to delocalize their electron onto. If we had them in a polar solvent, they would be more likely to form. We could reduce the energy barrier, but we are inside a solid polymer. We don't have a choice here. As you'll know, once we've got radicals in our reaction pot, a whole lot of things can happen. So one of the things that can happen is our radical here, so this is the oxygen radical, can attack and abstract a proton, so it can steal this hydrogen, but the radical isn't destroyed. We haven't managed to saturate the two electrons again. We've got one electron here, and we have to steal one electron from this bond, which leaves this bond having one left. So we transfer the radical to a new polymer chain. So we can do that. That's fixed this to a hydroxy group. So it's made this lower in energy, but it's excited the other chain. So we can do that. It's one of the possibilities. If two of these radicals are close to each other, either with an oxygen in or without, they can form a bond that destroys the radical. So that's a chain termination reaction. So the radical is now no longer existent. We've got rid of two, but we have formed a cross link between our polymers. So whether this is a chain termination reaction or whether the radical is still in existence, so whether we attack a bond inside the polymer and create a link between two chains but keep the radical alive, is dependent on how many radicals we have and how close they are to each other. This is a possible chain termination, but as you can see, we've cross-linked the polymer, and as you would expect, the polymer becomes harder and more brittle, more likely to break, and that's what we see in polymers as they degrade in sunlight. So the other alternative, once our polymer has reached a certain saturation of radicals, is that this oxygen can form a new bond, breaking this bond in the chain of the polymer. So chain scission, that forms a double bond here and a double bond here. So we form the ketone or aldehyde, depending on whether anything is attached to it or not. And we form a double bond here. Note, arrow, there's an unresolved radical here. So we need another chain to deal with that. It's unclear. It could do a whole lot of other things. So this radical has to do something. It has to interact with another chain. But the process gives us a broken bond in the structure of our polymer. So that is what we see, for example, if we watch an elastic band, which is a natural polymer, but without any heteroatoms in it. An elastic band, if we allow it to degrade, what we will see, if you keep it, find one in a drawer, you'll see that it becomes more brittle initially, particularly at the surface. That's where it's cross-linked. Becomes more brittle, less stretchy. But if you leave it too long, it cuts into tiny sections and goes all slimy and sticky. That's these small sections of polymer, particularly the ones with the double bonds on. They become a sort of liquid. So we go first of all to higher molecular weight, and then we go to lower molecular weight, is typical for polymer degradation. What we established is that this step is the rate determining step, and so we need to know how we can influence it. So if we want to make more singlet oxygen to make our polymer degrade more quickly, we could put a photo dye in there. Normally we would take our oxygen and we would excite it with ultraviolet light. That would be a transition from here to here. That's way more energy than we actually need because we only need to flip one of these electrons over. However, as we know from physical chemistry, it's quantum mechanically not allowed to flip an electron with light because it doesn't have angular momentum, not enough to flip an electron anyway. But if we have another molecule in play, the spin angular momentum of the orbitals can interact with the electron and help it to flip over, and we can do that in oxygen at a much lower energy. So we can cause singlet oxygen to be formed. That singlet oxygen would be when we flip this electron over, but it's even better if we pop it into this other orbital. That's the first excited state. If we take our singlet oxygen, or if we want to make our singlet oxygen, a typical photo dye would be an organic molecule that can absorb blue light. We can destroy our singlet oxygen or our radicals, so we can reduce the concentration of the radicals in our polymer by adding radical acceptors, which will take single electrons and make them harmless. The problem with radicals is once we've got them in our polymer, they hang around and they're really reactive, so they will find something to react with. But if we have some radical acceptors waiting to absorb it, then they will break the chain. We have those in our body because our body is exactly the same. The thing that makes us age, things that make our collagen become less elastic with age, is also the same process that destroys polymers. So we also have antioxidants that our body uses to accept the radicals, particularly the hydroxy radical, to reduce their danger. So this is an example of a radical absorber. It's PPD, paraphenylene diamine, which is a common dye in the hair dye. It's also the color in henna, and it works by the same process. So it loses an electron, so it can give a single electron to a radical to completely get rid of it. It then becomes a radical on the nitrogen, but then it can rearrange to form a radical on this carbon, and it can then rearrange again to form a radical on this carbon, and obviously this one is equivalent to this one, so this radical can be on the nitrogen, on these carbons, or this one here, one of 4 centers, so the radical is effectively delocalized across 4 atoms, which makes it a lot lower in energy and a lot less likely to react. Because the molecule has a second nitrogen, it can be oxidized again to form the double bond at both ends and to get rid of the radical entirely. And because the single radical intermediate is low in energy, it can hang around and wait, move around the polymer, for example, and wait until it gets a second electron, which makes it a radical acceptor. But other radical acceptors include vitamin C, vitamin E, for example. Typically, if one was formulating a polymer, you would put some radical absorbers into it to make it last for longer, because these will protect it against oxygen damage. So the next point of interest is, how do we catalyze this reaction? This is the lowest rate step of our whole chain, and so if we want to make it happen quicker, we would need to catalyze this reaction. And one of the easier ways to do this is to make it form a single radical instead of 2. As we can see here, we're forming a hydroxy radical and this carbonyl radical, and what we would like to do is cut it down so that it forms 1 radical at a time, which means that we need to donate or receive a single electron. We either need to give this an electron or we need to take one away. It doesn't matter which. So we need a species that can do that. We just had one that can absorb 1, but we would like one that can absorb it and then give it back again, and that doesn't block the reaction. So we need a slightly different one. A metal center that can have different oxidation states is an ideal candidate, So let's have a look at those. So the most common one and a very simple one to use would be iron, which can change between its 2+ state and its 3+ state by transferring one electron, either up or down. This is also typical inside our body. Inside our body, most of the iron is in its 3+ state, and our body has a host of chemicals whose job it is, and it's their only job, to make sure that the iron stays in the 3+ state, because if it can keep transferring to the 3 and the 2 state, it can cause these reactions to happen and make us old. So these are mostly hindered by chemicals that force the iron to stay in the 3+ state. Obviously, if we want it to happen, we want this couple to be active. So in one part of the reaction, our iron center will give an electron to a peroxide to make one of the radicals go away effectively, this one here, to turn it into a hydroxy anion instead, a hydroxide ion, and that makes an iron 3+ and a hydroxide ion and one radical, which gets rid of one of the radicals that we would have otherwise had to make. That lowers the activation energy, which makes the process a lot faster, but it gets rid of one of the ions, so we need that back. It's a catalyst. So this is the other side of the reaction, the published version of it. So if we take iron 3+ and we give it another electron, we can break this bond instead, which gives us a radical here, the ROO radical, the peroxy radical, and it gives us our iron 2 back. It gives us a proton, which obviously would interact with that OH- to form water. So we've made water out of the end groups of our peroxide, and we've made 2 radicals which are on the chains, but in 2 steps, which reduces the energy. This puts us into the ethical part of this question. So if we do this, we are doing the same thing that polymers would otherwise do, just faster. And that has positive and negative effects, lots of them. So if we do a degradation of a polymer that's quicker, it's obviously good for the environment. It will turn into ketones and aldehydes, which can be respired by normal organisms, so they will eventually go away. On the other hand, we will make microplastics very quickly because our polymer will get brittle and it will break down into small parts and they'll flow around. If our catalyst is an iron catalyst or a cobalt catalyst or a manganese catalyst, but mostly if it's an iron catalyst, it will be completely harmless to the environment. So if we consider an oxo-degradable conventional polymer and a biodegradable polymer, so a completely different polymer, and think about how they will interact with our human society, we will see that there are positives and negatives of both sides, and it is not very simple. The first thing I would like to think about is how do they interact with a recycling process. So if we take an oxo-degradable polymer and we throw it into a recycling process, what happens? Well, if we do that, the additives will be watered down in the polymer, and it will make the polymer slightly worse. It'll make it degrade slightly faster, but not very much. During recycling, you would typically add some antioxidant anyway, and maybe remove a few of the shorter chains, and so it's not that bad. So we can recycle our oxo-degradable polymer. Biodegradable polymers typically aren't recyclable, or at least they're not compatible with conventional polymers in a recycling facility. So if we consider a polyethylene oxo-degradable polymer, so one that's had some additives added to it to make it degrade, we can throw it into the normal recycling process. Normal, it's not super common in the world. It can be recycled with polyethylene, it can be mixed in any amount, and it won't damage it too much. If we have a biodegradable polymer made of silk, starch or something, it is not mixable with normal recycling. It has to be biodegraded, or it might be recyclable, but it's unlikely. Most of them are not, because they're not very easy to remelt and reformulate. Usually they degrade comparatively quickly, which brings us to the next point. How do we can control when and how quickly it degrades? The oxo-degradable polymers, all we have to do is vary the amount of additives that cause them to degrade faster, and the other additives, the antioxidants, that make it degrade slower. So easy-ish to control, can be controlled. Whoops. Controlled. Biodegradable polymers, the problem is it starts when it gets damp. So starts immediately. They can be controlled to a certain extent, and we will get onto those, but the starting of the process is more difficult to stop. Nothing happens till the antioxidant has run out effectively, and then they suddenly start, which is practically better. These we can make degrade slower or faster, but they do start to degrade immediately they get wet, which can be a problem. It's not a great problem, but it is something that determines which ones are better for which purposes. So now I've added products on both sides and conditions on both sides. So if we take an oxo-degradable polymer and start to degrade it, we will make interesting and weird short chains of polymers with broken double bonds with oxygen groups on. They're not really toxic, but they are sometimes not common. So if we have side chains on there, they might be slightly toxic. They might cause growth to be stunted. There is a debate about that depending on what the manufacturers have done, and it is quite complicated. If we take a biodegradable polymer, it will also break down. Typically the products won't be that bad, but they can interfere with natural processes, so they can also cause problems, usually not as bad, but it depends on the exact biodegradable polymer and the exact oxo-degradable polymer. We have the conditions, which is slightly simpler. The conditions of oxo-degradation is that oxygen is present to start with to generate oxygen radicals on the material, and then it just has to be warm. Once it gets broken into smaller parts, then it needs to be live. There needs to be something to break down, biodegrade, because these are typically called oxo-biodegradable. So the oxo cuts the chain into small parts, and then it becomes biodegraded. The biodegradation has to also happen. Otherwise we end up with some chemicals, sort of a sticky mess, which is what you tend to find in the drawer in your house, in your student house, where the elastic bands have been kept for years. There will be this sticky mess. That's because it's broken down by the oxo degradation pathway and the products have nowhere to go. If it was in the ground, they would be degraded by bacteria. So typically the oxo conditions are presence of oxygen, presence of UV. So this works better in light. So typically if we have a plastic film for farming, it will be oxo-degraded comparatively rapidly. If we bury it under the ground, there is little oxygen and little UV, little mechanical action, and the bacteria are not very active. So then it will take a very long time for this to do anything. If we have a biodegradable polymer, then it needs to be in conditions where there's enough water and enough bacteria to do the degradation. So the problem being, if we have polylactic acid, for example, that we want to make 3D models with, we can't keep it in a normal room for a long time because the humidity of the room will cause it to start to degrade. That won't cause it to just disappear, but it will reduce its properties over time because it will cut the chain into smaller bits. Biodegradation does not make it more brittle to start with. Oxo degradation does. So we would expect this to become more and more liquidy and not to get more brittle to start with. So it is, from a materials point of view, not very easy to answer with a single product. Is an oxo-degradable polymer better or worse than a biodegradable polymer, and better or worse than a conventional polymer? In an ideal world, conventional polymers would be purified and recast, would be recycled, and there would be a perfect cycle of use until there was enough damage to them, until there was enough oxo-degradation accidentally to them that they became useless, and then they would be processed into new products. So they would go through a chemistry process to make them, either completely burn them to make energy or to make new things out of them, so a return to monomers. That's not what we've really got. We've got a process where material is continually being added, material is continually being lost in bad ways. Polymers are lost into the sea, they're lost onto the land, they're buried in landfill, and where they end up determines which one of the possibilities is better and which one is worse, because oxo-degradation will happen anyway, but it's obviously better for microplastics if it happens faster. But if the microplastic ends up at the bottom of the sea, there isn't a lot of oxygen and there isn't a lot of UV, but actually none, at the bottom of the sea, so it's not going to be oxido-degraded down there. If it is on a farmer's field, there's plenty of UV and plenty of oxygen, and so it won't last very long. So it depends very much on the conditions and the use of that particular item, which is the best answer, and it also depends on how good the recycling is. In a very good recycling area, oxo-degradable and biodegradable polymers have less argument for their use, because recycling is an excellent way to deal with polymers. Okay, so oxo-degradable polymers are an ongoing subject and an ongoing subject for debate, because it is never clear when they're most useful, what damage they do, whether they do any damage, what we can do to modify it, and how they interact with other problems such as waste, landfill, microplastics, washing, all of those kinds of problems. So there was a bit of materials degradation for you today. We'll go on to something else next time. See you again.